Okay, so one of the reviews that might be necessary for things that we're about to study are a couple of integration techniques. So these were covered in SAT 194. One of them is called the substitution rule, and this is sort of like the chain rule of differentiation in reverse. And then the other one is integration by parts, which we'll cover in the lecture. So the substitution rule for integration, as I said, is sort of the reverse of the chain rule for differentiation. Now when we have something, say, like this, and we want to find dy dx, so this is our function, and we want to find dy dx, what we usually do is we think of it as having an inner function and an outer function. So we say that this equals u to the half, where u equals 3x squared plus 2, like this. And so we first find out what the derivative of this is with respect to u. So this dy with respect to u gives us, and it's just half u to the negative a half. So just the rule of multiplying by the power and then subtract 1 from the power. And then we also find du dx. So du with respect to x, so that's from up here, and that gives us 6x. And the way that we then represent it is we say that dy dx is equal to du dx times dy du. And we can see it's sort of in an algebraic type of way. We get kind of like a cross cancellation of the du's there. But usually when we write this, there's not need for all of this notation. We can just go straight to, say, the inner 3x. So this is going to be 3x squared plus 2 to the negative half times a half. So that's multiplying the inner, this u to the half, so this outer function, I guess. Now multiply it by the derivative of what's inside, which is 6x. So neatening this up, I would have 6x cancels with 2, so I have 3x all over the square root of 3x squared plus 2. Now, when we're going backwards, so say we're going backwards here, and we want to find the integral, and I'm going to write it slightly differently, so I'm going to write it as 3x times 3x squared plus 2 to the negative a half. So when we're going backwards, what we need to recognize in order to use the chain rule is that we have a function here which is some multiple of the derivative of what's inside there. So that we can then say, okay, I recognize that I have the derivative out here, and that's how I make a substitution. So we want to keep that in mind when we look at this rule for integration. So, say I want to find the integral of, now let's just say it's, let's do it with this function here so that we can see the direct correlation. So I want to find this integral. Now what I do with substitution is I say let u equal 3x squared plus 2, and therefore du dx is equal to 6x, which means that I rewrite this so that I have du equals 6x dx. Or sometimes what I like to do is, what I'm going to want to do is replace these bits here, so I can try to get it in terms of this 3x here. So I can say du on 2 equals 3x dx. That's how I like to do it anyway. So I have these two sets of substitutions that I can make into this original integral. So it becomes du on 2, so that replaces the 3x and the dx, because that's what that's equal to here, and then substitute the u back in for here, u to the negative a half. Or, sort of a half times u to the negative a half du. And this is an integral that we can deal with because it's just a constant multiplied by u to the negative a half. We can use the power rule. And so this, as an integral, becomes, I add 1 to the power, so it becomes u to the half. And then I divide by my new power, so I divide by a half, and I just get u to the half plus constant of integration. And so if I now substitute back in what I know u is equal to, I get that this must be 3x squared plus 2 to the half plus c, and that is my integral. So what we usually are required to do is first recognize that it's in the form of where we have an inner derivative outside of some other function. Let's have a look at one more example. So where we don't know the integral. So let's say I wanted to find the integral of x squared sine of x cubed. Now again, what I say is I've got sine of something. I might put that in brackets to make it a bit clear. I can say I've got sine of something, and then the derivative of this is out here. So the logical substitution that I make is that u equals x cubed. And then I have du equals x squared, 3x squared dx. Or one thing that I usually do is, since I've got an x, only x squared here, not 3x squared, I just divide through by 3, so I get du on 3 equals x squared dx. I make these two substitutions, so my integral now becomes sine of u on 3 du. And integrating this, the integral of sine of u is just cos, negative cos of u. We just have the constant here, plus constant of integration. And so I'll have negative a third, if I want, cos of x cubed plus c. And that's my integral. And we can verify that if I differentiated this, then I would get up to here. So it works like that. Now, the other thing that we sometimes need to keep in mind is just that what we do with our terminals if we've got definite integrals. So I'll do one more example, but in this case, let's have some terminals. So say I want to go from 1 to 4, and the function that I want to find the integral of is maybe, let's do cos x times e to the sine x. Put that in brackets. Dx. Yeah, I want to go from 1 to 4. So I create my so I can create my substitution. Now again, here I've got the derivative outside of a function of another function, so I'm going to let u equal sine x du equals cosine x dx. So my integral, without the terminals, would be just e to the u du. Now, one thing that we can do is just leave these terminals blank, find the derivative, which in this case is just e to the u, and then I can wait to make my substitution and put my substitution back in, so I've got e to the sine x between 1 and 4. And do it this way. However, what I can also do is if I've got u equals sine x and I'm going from x equals 1 to x equals 4, then I can actually change my terminals if I want. So actually make it from, we're going instead from u equals sine of 1 to u equals sine of 4. These are a bit weird numbers to have with sine, but that's okay. And then so here I can actually evaluate this between sine of 1 and sine of 4 if I want. With u equals, and it's actually up to you which way you do that, because doing it from here, then once I've got it in this form, I'm just going to be saying it's e to the sine 4 minus e to the sine of 1, and in this case exactly the same thing. Okay, so it's probably worth doing a little bit more research on this if you want more practice. So it's called integration using the substitution rule. So you can look up a few examples. I might put up some pages of notes from a textbook as well.